Yeah, we
Here we go. Oh, great. Apparently we're lecturing for them. We'll change that for
Okay, let's get started. So, I think we're making decent progress, and I will spend another 5 or 10 minutes today to wrap up the discussion on SQL, and that will complete our review for the application layer of the database system. Then we will dive into the kernel, and hopefully later this week I will be able to release you project 1. And at that point, I will also check on the status of your team matching, right? Whether you have found a teammate. I'm also debating whether we will do a 2-person team or 3-person team, because the project is comprehensive. It's a very comprehensive coverage of database kernels, and it does require fairly long coding and fairly good programming skills in order to work on it. So it's system coding. I don't know how many of you have ever written any code in a real system kernel. Rather, most likely you've been working on some kind of code that's more or less a standalone application for implementing some particular algorithm. Typically, the design of the algorithm might be hard, but once you know the algorithm, implementing the code is trivial in most cases. In our case, is a little bit the opposite. I mean, both a little bit both. The algorithm might not be trivial, as we will see later on in some of the system kernel discussions. And even if you know the algorithm, you know what code you want to write, just to figure out where to write that code, which line to modify, which line to insert, that itself becomes really, really tricky. Not easy to do. I remember when I was an intern at Microsoft back in 2005, and they were busy trying to release SQL Server 2005. They released later in the fall. I was there in the summer, so they gave me this. The second internship. The first internship I didn't work on the kernel code. The second internship I was in the database group in 2007, summer 2007, and they were trying to release SQL Server 2008. They gave me the entire code base of Microsoft SQL Server. It took me about a week to figure out to insert a line to just say plain hello world on my terminal, because you just cannot figure out where to add a line that will be part of the sequence of execution and lead you to that terminal output. It's that hard, okay? It's that hard. So our system is not as hard as that. If it is, I think we can build something and sell for money after this class. Everybody will get a share, and then everybody become rich. Right? Unfortunately, our system is not as good at that yet. That's why it's called simple DB. But functionality-wise, it's very close to a commercial database system, like something similar to PostgreSQL, as you will see later on. That said, let's continue. So last time we said left outer join, right outer join, full outer join. The idea is that it's similar to an inner join. An inner join is simply a theta join. It's same as select, from, and where clause. It's just a more convenient way of expressing the same thing using the inner join semantics. But outer join is something different. Outer join produces a full manifest of a table on either the left-hand side or right-hand side or both ends. Even for those records who do not match the join condition with respect to record from the other side, When that happens, you simply use non-values for those attributes that come from the other side that this record do not have a matching record for. You join conditions, okay? So that's the outer join. Next, I'm going to introduce something called the views. So view is a very useful construction in the system for mainly for two purposes. The first purpose of view is to simplify your query writing. So the idea of this is that you have a bunch of tables in your database, but sometimes you need some additional information on certain records, on certain objects in your database. Those additional information can be obtained by writing a complicated SQL query involving join of multiple tables and so on and so forth. So one solution would be every time you need those additional info, you just write that same SQL query again, or write a new ad hoc query from scratch, which is fine. But what if this is something you constantly need, right? You always need this piece of data. You always need to do this join. One argument would be, okay, why not you produce another table in your database? But then this goes against the design principle of normalization, which is you want to keep minimal amount of information in your data, in your database, and you want to get rid of any potential duplicated redundancy information in your database, because redundancy is the evil of database. I'll argue that for you, right? So whatever information that can be derived from your base table, you don't want to store them as another additional table in your database. Does that make sense? So for example, I want to know, for whatever reason, right, this owner of the Sailors Club wants to know the number of reservations made on red color boats. And he or she wants to check on this every day, or maybe twice a day. He or she wants to check on this piece of information. This information obviously is available from by joining the both table and the reserve table. You can report back for each red color boat how many reservations has been made on that particular boat, which is simply this query, right? Select boat ID count from both reserve, join on boat ID, and color to the red, and group by boat ID. That gives you the count on the number of reservations made on each red color boat. So one solution would be, whenever the owner of the club wants to know the number of reservations made on any red color boat, you write this SQL query, you execute, you get the results back. But then, here is the inconvenient part for you. You have to write this SQL query from scratch every time. Does that make sense? And you cannot store this at another table, because if you do, then you are storing redundant data, data that actually depends on some other data in your table. Because if you do store this at another table, then whenever a new reservation is made on existing red color boat, or whenever a new red color boat is inserted into the Sailors Club, that this new table would have to be updated. So the data stored in this quote-unquote new table will be completely redundant and unnecessary. Okay? So for that reason, people introduce something called the view. Semantic is create view. You give a name for the view, then use the keyword as, then use a SQL block as the definition for that view. Okay? Once this being defined, you can then, so this is an example of this. If that's your base table, and I didn't show the reserve table here for some reason, then that's the output of this view. That's the output of this view. But keep in mind, this output here is really conceptual only, right? By default, you do not materialize this into a table. You do not materialize this into a table. And once you have the view defined, then you can use it in your subsequent SQL queries. For example, you can then select from red and bold and find those with reservation less than 10. So what does this query do? Right? If you look at the view definition, what the following query does is report the name and the number of reservations made on that boat for all red color boats that has less than 10 reservations. Report the name and the number of reservations made on that boat if it's a red color boat and has less than 10 reservations. That's essentially what the query at the bottom does. You follow me? Now you can appreciate the point I was making earlier better, in the sense that it does help simplify your query writing, because otherwise you will have to define this graph using this group by query clause. Does that make sense? But here actually introduce a really interesting challenge to the underlying database engine, right? The naive way to understand this query will be, whenever I see the name of the view, what do? You substitute, the database engine simply substitute the view with its definition, meaning whenever I see the red here, I will simply replace this whole thing with a bracket, then select this whole thing, closing bracket as R, then both speed, carry on. You follow me? That will work. However, it is not efficient. If I were to tell you to write this query from scratch without you knowing this view, what would you do? You would simply write a group by and heading query, which is you simply write something like this, right? Okay? Note that I add the boat name to the group by clause. This is a little trick I explained last lecture to satisfy the syntax requirement of group by, so that it enable you to having boat name in the projection list. Because everything there must be either an aggregation attribute or part of the grouping list. And group by boat ID and boat name is the same as grouping by boat name. Boat ID, because boat ID is a primary key and a foreign key in the reserve table. Okay?
Does that mess anything up if there's two boats with different IDs but the same name?
It will not, because you're grouping by the combination of them. So they will end up in different groups.
Okay.
The fact that they have different boat ID to begin with, right? Even if they have the same name, they will still end up in different groups. That's the thing. Fundamentally, that's probably because you didn't take my undergraduate class. There's something called functional dependency. On FD, there is a functional dependency that says boat ID determines boat name. Okay? There is this functional dependency right there. Okay? So if you compare this against substituting rest directly with the definition of rest, clearly this query is much more efficient. Because why would you do a group by, then join yet again to find out it's less than 10 when you have heading readily available while you're doing the group by? Obviously this is more efficient. This brings up an interesting question, which is, something called query rewriting, which is, yes, conceptually that's what you do, but can the underlying database engine be smart enough to figure out when I substitute the definition of view with its definition is actually equivalent to a simpler query like this. Bottom line, query writing, the objective query writing is to reduce the number of joins you have to perform. Typically, when you use a view definition as it is, substituting the view definition in SQL query that uses the view, it ends up with many joins. For example, in this case, there is a join between the view and both. So the objective query writing is really to reduce those unnecessary joins when you do that substitution. Okay, and this is a very tough problem, actually. It's a very deep problem. So I will stop right here. Later on into the course, when we learn more about the query engine, I can come back and visit this topic a little bit, in a little bit more depth. Another point I was trying to make, okay, is that okay, you do this substitution of the view definition when the view is not materialized. The keyword is materialized. When a view is materialized, what that means is you actually store this table, the data of the view, somewhere in your database. So it becomes a physical table somehow. In that case, if that's the case, do you still need to substitute the view with its definition? No, you do not have to. If that's the case, you do not have to substitute the view definition anymore because there is a table with the view data readily available for you to use. You treat it just as another table. Do you follow me? So in that case, you do not substitute the view definition. Then you do not have to worry about this challenging problem of query writing, reducing the number of joins, all that stuff. You may argue, okay, sounds like that's a better approach. Why don't we always materialize the view? Why don't we always materialize the view? Well, then I have other problems. If you do materialize the view, what's the problem? Well, the evil of redundancy kicks in. Right? Remember, view is a view because it simply stores redundant data. So whatever data available in a view is dependent on the existence of some base records from some base tables in the database. In this particular case, this view red, the data here solely depends on data from reserve and bolt. So whenever you have updates to either bolt or reserve, you may have to update the view. In this case, it's just one record, it's not too bad, but imagine in a million record database, this could be really, really expensive if you try to materialize the view. So there is this trade-off between efficiency of update and efficiency of your query. Typically, when you do materialize the view, the efficiency of your query becomes better, but the efficiency of update becomes so bad. If you do not materialize the view, then you have to deal with this challenging problem of query writing, which has been shown to be an NP hard problem, unfortunately. Meaning, if you try to rewrite the view to find its optimal form, optimal reduction, to find the optimal reduction is not trivial. Okay? So we talk about order by and limiting the output to top 10 or top K. So I will skip this slide. Another useful thing the view does, in addition to simplify your query writing and make it easier for you to read about your query, right? Think about view as kind of like the renaming operator in relational algebra, essentially. Right? Beyond that, another very useful feature of view is that it helps you define access control to your database. So access control is a critical requirement for any database, right? Because database stores sensitive data, banking data, FBI data, or universal Utah data. Student data is sensitive too, right? So you do have to make sure right people have access to right data, right? So how do you achieve that in a database setting? Well, this is something called the concept of privilege. I'll use this simple slide to explain what's going on here. So what you do is you have different kinds of privileges. So such as select, insert, delete, references, and all. Okay, this shows you what kind of privileges you have on a database, on any database object actually. So you can use this grant statement to give a particular type of privilege to a particular user on a particular object. That object can be a database, can be a table, and what's more interesting, can be a view. Can be a view. Okay? Can be a view. And let's ignore the with grant option for now. So now you understand the way I limit user account, which is CS6530 user, I limit the access of that user to our database server is by using this statement. I only grant select privilege on DVD rental on that database to CS6530 user, so that that user only has select privilege on that one database. By default, you do not have any privilege on any objects in the database. As a user of the database, you have nothing. So only when super user, so I'm a super user of the system, when I start giving out privilege, you start to gain access to certain parts. So by default, you have nothing to access to. You follow me? Now, the important message here is to remember that object can be a view, and the fact that by default, a user has no access to whatsoever to anything on a database server. So what that means? That means using by leveraging a view or multiple views, I can control access to any user with really fine granularity to any data on my database. For example, I can even define a view that reflects to just a single record from a particular table. For example, I can define boat 103 as select star from boat where boat ID equals 103. Then I say grant select on boat 103 to user A. What that means is this user A can only read any value of this boat 103 but nothing else. A single record in your database. I can even do a single cell, for example, boat 103 name, which is defined as select boat name from boat where boat ID equals 103. Then I can grant select privilege on boat 103 name to user A. You can only read the name of boat 103. Nothing else from the database is open to you. You follow me? So using the view, that's the second important usage of view, which is to really do access control to a database, to do fine granularity control over access to data. Okay. Now, lastly, what's that with grant option? What that means is if I, as a super user, grant privilege to a particular user on a particular object, that with grant option tells whether that user can in turn grant the same privilege on the same object to another user, whether he or she has the ability to do that or not. You follow me? And this brings up an interesting problem, which is when you do grant, you must have a way to revoke access control later on, right? So a particular access right later on. And that is done using revoke. That is done using revoke. Okay? That is done using revoke. And when you revoke a privilege on a particular object from a given user, what happens? Do you revoke that immediately, or you have to do some checking? Well, the fact that you have this grant option complicates this matter a little bit more. So the reason is, suppose this is a super user, okay, and this is the user A. Then super user say grant a particular select privilege on particular object 1 to this user, and that's it. Okay, but I also did the same thing. I denote this whole thing as X. I give this privilege to another user B, but now with grant option. Right? What that means is user B can, because I gave user B with grant option, so user B can give X to user A as well. You follow me? Only X, nothing else, because you can only give privilege that's given to you with grant option, not anything additional. So later on, if I decide to revoke X, so this forms a graph, if you think about it. Later on, if I decide to revoke this, so this X is kind of cut off, right? But that doesn't necessarily mean user A no longer has X, because I may obtain X from yet another path. You follow me? So this becomes a really tricky problem. I mean, for small database, that's no problem. But if you have many users, many objects, many views, and many grant statements have been issued, especially with grant option, you have to maintain this graph structure somewhere in the kernel to understand what's going on, right? So there is an interesting graph problem right here as well, okay? All right, so I think we kind of understand the discussion. Let me show you the, okay, so I will connect to our database, and I will show you all the views. So it has different schemas, the name and so on and so forth. This schema column is not the schema as we understand from the relational model. When we talk about schema in relational model, we refer to the definition of a particular table. This schema column here refers to something else. I will later explain today. This belongs to system catalog. Okay? And let me show only those from public. So these are the views defined on our DVD rental database. If you compare this against tables, so these are the tables of the DVD rental database. Okay? And there's one view I want to show you, which is actor info. So I can describe that view. Okay? So this is a view, and the definition of the view is available from here. You see that? So as you can tell, this is a fairly complex definition, right? Do you follow me? Because it's trying to get the film info for all the films the actor played a role at, and use some fairly sophisticated functions of SQL, such as concatenate. That stands for concatenation. Concatenate multiple output, forming a new string as the output that goes to the film info column. Do you follow me? So imagine if you were to type this yourself every time, it's very inconvenient, obviously. So instead, I can simply do select start from info. I don't know whether this view is materialized or not. I don't know about that. So either it is going through a query writing process where you substitute the actor info with its definition, or if it has been materialized, it will simply execute this against that materialized table. And this will be the output. And this is kind of hard to read. Let's get only the first record. Okay. So obviously that shows you the first name, last name of this actor, and all the films. I believe this must be he that he plays a role at. You follow me? Yes? And compare this against the base actor table. So you only have the first name and last name information. Now where that third column come from, the film info come from? Well, it's come from the film table and a complex joint between film and actor. Follow me? So that's the view. The privilege, let me see, how do I show? I forgot how to show privilege in PostgreSQL. The other thing I want to show you is this concept called triggers, and also how to use SQL in another language, like in Java or Scala or Python or PHP. These two topics I'm not going to cover it in this class because these are more on the application side, which I cover in detail in my undergraduate class. Right? If you're interested, you can review them yourself. But I do want to mention trigger a little bit. Trigger is a procedure that starts automatically if specified change occur to the DBMS. So it's similar to a daemon process running on a Unix or Linux or Windows operating system. So it runs on the back end, and it only comes to action when certain condition is met. And there are three components in a trigger, which is event, activity that trigger the trigger, and condition. It doesn't mean whenever some event has occurred, trigger will take action. Trigger will check this condition when certain event has happened. Only if the event has happened and condition is met, I will take action. I'll give you a simple example. I will turn on my TV and watch for US Open. That's my action. Turn on TV and watch US Open. If it is sunny today, so I don't like to watch matches that go under rain because the quality of the play downgrades, right? So doesn't matter. Even if number one plays in number two, if it's not a sunny day, I'm not going to watch it. Okay, so that's the condition, which is it's sunny. What's the event? Well, the final is today. So I'm going to watch final game. So that's the event. So when it is final, that's the event that would trigger the check of the condition, which is it is sunny or not. If the condition is met, action, turn on TV, go watch it. You follow me? Okay. So logic-wise is very simple, right? The matter is really boils down to how do you express this in a database system. While different server has different configuration and different specification for this, I can show you a simple example of this. So I want to make sure, for example, the minimum salary for professor must be 100K. You know, 100K is actually not a lot of money. So let's say professor has to make this much, which is already, in my opinion, bare minimum, right? Very little money, right? So just 100K. So whenever you try to insert new faculty with salary less than 100K, you know, reject it. Okay? Do not allow the insertion of that faculty. With a message to the university administrator, you guys are treating your professors so bad that nobody's gonna work for you. Okay? So I want to do that. And I want to make sure this happens before. You guys might laugh on this, but 100K is really nothing compared to, especially for CS professors, right? If you go to Google, if I do decide to go to Google Office, I can easily triple or 5 times my salary easily. And what I'm making now is seriously just peanuts as what I can make if I work for Google and and these companies. Okay, no kidding. I'm serious. Okay. All right. So I create a trigger. And I give a name for the trigger. I say before insert on. So that's the event. The event is before an insertion happened on the professor table. And then for each row, this particular syntax is a generic syntax. Okay. So different database server has different language for you to specify when and if and else and begin and so on and so forth. But you get my point, right? So what happens is for each row, new, typically in most database server, new stands for the new record you are trying to insert. So new is a handle points to the new row that's just being inserted, attempted to be inserted. And you check the salary, if it's less than 100K, you raise a message. Okay, let's see that in action in PostgreSQL. So actor, for example, has a trigger. You see this? So actor table has a column called last updated. So if you recall, I tried to insert an actor named Feifei into the actor table the other day. And I didn't specify a value for last update, yet I still can. I didn't specify this value here, but automatically a value is populated into that record. Did you notice that the other day? When I inserted this record, I never specify, I never like take out my iPhone and take right on the time and enter that time value there. My iPhone won't be able to tell me this actually. 40 seconds point. I mean, this is amazing, right? 0.216. I don't know why somebody would care you insert that, after so many milliseconds. But anyway, so my iPhone even cannot tell me that. Maybe some app will do that, but the default app of clock won't be able to tell me that value. So obviously I didn't enter that value. So somebody automatically entered that value for me. And now you know why, because there's a trigger defined. And it happened before update. So whenever you try to make modification to the database, before that modification is honored, for each row, here, for each row refers to for each row being affected by the update, rather than every row that exists in your table. An execute procedure, then there is a procedure called last updated. You follow me? Let me see whether I can find out the definition of that procedure. So it's right there. What do you see? Procedure, the way I do this is df. Why? Procedure is considered as a function. So df will stand for display all functions from the public schema. Or I can do to display only that. That's updated. Okay, so it shows you that this is a trigger. If I want to view the definition of this function, so that I can see the definition of this, and it shows you that new, basically for each new record, the last update equal to current timestamp. Period. Return. That's it. And they use language called PL, PJSQL. And this is something very interesting I'd like to mention is most database systems support a language syntax called PL/SQL, Procedure Language SQL. And if you go to any banks, any like Wall Street banks, they all use PL/SQL to define functions and procedures. So whenever somebody tries to design a new database system, it's critical for you to support not only SQL but also PL/SQL, so that their legacy code can still be executed without any modification. So in PL/SQL, the syntax is similar to what I showed you right here, begin, end. There are also syntax for if and else. They support if and else, for loops. It's just like a high-level programming language, written in a SQL-like manner. Okay? Any question on triggers? Last, I want to show you the privilege. I forgot how to show that in PostgreSQL. So when you forgot to do something, your best friend is Google, right? Okay, just dash out. Okay, good call. Oh no. Okay, so no, I don't want to show this. I want to show. I forgot how to do that. I will figure that out and show you next time. But there's a way for you to show the current users and all the privilege that have been given out in PostgreSQL. Okay? That being said, that's it. That's the end of the discussion on SQL. Okay? So let's move on to the next topic in our discussion. Okay, so all right, so we are done with the review of the application layer. Now let's dive into the kernels. Right? Let's understand how we build something similar to PostgreSQL, which is what you will be doing fairly soon, starting maybe later this week or next week. You will start building a mini PostgreSQL essentially, called SimpleDB. And in order to do that, we have to understand how the kernel works. And we will take a bottom-up approach. So far, we take a top-down approach. We talk about relation algebra, relation calculus, relation model, SQL. But now you understand, in order to understand what happens after you type this, what happens when you type enter? In order to understand that, we take a bottom-up approach rather than top-down approach. Okay? So when you do a bottom-up approach, the first thing, of course, is to figure out where data are stored, where tables are stored, how they are organized, and so on and so forth. So that brings up the topics on storage engine, buffer, and files. So we call database as a database system, right? Database management system. So the first question we ask ourselves is, what is a system? What is systems? System is not programming. It's not programming big, complex things. Many students say system is just about programming and programming a lot. Read a lot of code, that's system. No, that's not system. When you read a lot of code, not necessarily that's system. System refer to the efficient and safe use of limited resources. Pay attention to the keywords I have highlighted. This is important because the first important thing to note is we have limited resources. We have to accept this. When you have unlimited resources, how you design your system actually become irrelevant. Why? I'll give you a simple example. Imagine we have a system where everyone can get whatever you want. You want $1 million house, I can give you. You want $1 million boat, yes, you get it right away. So that means we have unlimited resources, right? When you have unlimited resources, do you still care Do you still care how the tax system works? How you work to make money? You don't care about any of those, right? Because you have unlimited resources. Right? The fact that we have limited resources make us to design efficient, better, and scalable system. Right? For human society, that's whether you go with democratic system or a more authoritarian system, right? So human beings come up with these different designs to manage human society fundamentally because there is unlimited resources. That goes back to the time when human being first became human being, right? If you have unlimited system resource, then whenever you want meat, there's a tiger dive right in front of you, you can take meat. If that was the case, we wouldn't have human society. Everyone would be on their own, right? Why do we want to be together? Because they are weak. They cannot defeat the tigers. That's why they are together and figure out ways to organize into a little society. And that little society, essentially from a computer science point of view, that's a system. And you have limited resources. So that's point number one. Point number two, once you have limited resources, what happens next? Well, because you have limited resources, you want to make sure your limited resource is put into best use. That's the efficient keyword. You have to make sure you efficiently use those limited resources. If you only have $10, you don't want to squander your $10 on something that's not necessary. For example, if you only have $10 for a day, you do not use that $10 to watch a movie. You probably will use that $10 for a lunch, for a nice burger, right? But when you have $1 million, go watch your movie, go have your burger, whatever, I don't care, right? But even if you have $1 million, you probably won't say, okay, I want to launch a rocket today. Because a rocket will take you maybe $10 million. Even $1 million is relatively limited for you, right? Now, next, safe. Safe is important, right? So you have an efficient way to use your system, but you have to use them safely. You have to use them safely. Right? For example, you cannot write data to disk and assuming that data will magically store on disk permanently, nothing will go bad. And whenever I want my data, it will be back. I can retrieve that data back on disk because disk may fail one day, who knows, right? And same two users might write to the same file at the same time, so one may overwrite the other. So both of them might try to append to the last line, but this last line is a relative concept. Does that make sense? Depending on whose insertion, whose append operation happens first, the concept last line changes, right? So that's what we mean by safe. So that's essentially the objective of the database system, right? Which is to design a system, design a way to efficient and safe using of your limited resources to support those database operations. So we talk about those are the application layer things. Then we will look at these components that are more system-oriented. So the first thing we will look at is what we call storage media. For this, we will introduce what we call memory hierarchy. So, which is explained by this graph right here. So this is a very simple, dramatically simplified computer organization. You have CPU, you have your cache, and in cache you have level 1 and level 2 cache, and you also have data cache and instruction cache. Cache is implemented physically, is implemented by register. So it's really fast, but has really, really limited storage, typically in kilobytes or megabytes at most, right? And then you have your main memory, which is what we call RAM, random access memory, which is typically in the order of gigabytes. Then you have your secondary storage, which refer to our disk. So cache is fast, but it's small in size, and memory is also fast, but not as fast as cache. However, it's much bigger than cache. But both cache and memory are volatile, meaning whenever you lose power to your system or if your system crash for whatever reason, the contents of cache and memory will be lost when you recover from that system crash or when you recover from that power failure. One thing to note is CPU only operates on data in main memory. More precisely, CPU actually only operates on data in data cache, right? But for the purpose of this course, we will focus on the data transfer between disk and memory, and we will ignore that data transfer between memory and cache. At least for now. Later on, if I have time to talk about main memory database, that transfer becomes important. For now, we will simplify and have this abstract view that CPU operates over data in main memory. In reality, what happens is CPU will still need to bring data from memory to cache, into the data cache, and operates on data cache directly. Okay. So disk is much larger in size and is non-volatile because magnetic disk, if we are talking about magnetic disk, they use magnetic field to store 1 and 0 permanently. So even if you lose power or your system crash, data stored on disk are still there, are persistent. So it's non-volatile. And it's much cheaper. If you look at dollar per byte, disk is much cheaper than memory and cache. Okay. And there are other players as well, such as solid-state drive, also known as flash drive, flash disk. Some of you laptops may come with solid-state drive instead of hard drive. The reason for that is they support random reads much faster than magnetic disk. I will explain that in a minute once we understand what is random read and what is sequential read. But it comes with a price. Dollar per byte, solid-state drive is still much more expensive than disk. And furthermore, more importantly, the life of a solid-state drive typically is less than a disk. The reason is fairly expensive to do write, to do update for data over solid-state drive. I will explain this in further detail later on. Okay? And there's something else called tapes, which is really for long-term storage, which is even more slower than disk, but it's much cheaper than disk as well. But it only supports sequential read. It doesn't support any random read or random writes. So this come back to this picture after we see all these players. You can think about this as a summary of this memory hierarchy. The horizontal line there is the boundary between volatile and the non-volatile storage medias. Okay? And as you go up, you get higher speed, but you pay more price. When you go down, you get lower price, and you get slower speed as well. So you, once we understand this hierarchy, now you understand we have to worry about data transfer between different storage medias because you cannot have a single layer that holds all your data, and CPU only operates data at the very top. So whenever you want to process some data, you have to look for that data at the lower layers. And this introduces cost. And an interesting challenge, of course, from the system perspective is to minimize the amount of data transfer between different layers. Right? So that's kind of one of the major focus of any system. There are different kind of data transfer as I lay out there. Basically, from any two immediate layers in this hierarchy, you will have a data transfer. But only happen at two immediate layers. You never have a data transfer between disk and cache. That just doesn't happen. Only happen at two neighboring layers. Okay, data transfer. Okay. So theoretically speaking, we can abstract away all these details when you look at only the top two layers, cache and main memory. And when you also abstract away the cache layer, like I said earlier, if you assume CPU operates on data in main memory directly, assuming this cache layer has a small impact. If that's the case, theoretically, this is something called the RAM model, random access model. V stands for your CPU, and that rectangular yellow box is RAM. RAM is called RAM. Memory is called RAM for a reason. It doesn't call RAM for some arbitrary random reasons. The reason people refer to your main memory as RAM, random access memory. The reason is RAM, when you see you have a main memory, typically you assume that it has constant cost for accessing a memory address anywhere from your memory. Whether you're accessing the first 8 bytes or thousands, starting at the thousandth bytes, the next 8 bytes is always constant cost. If you're trying to access the same size memory unit, be 8 bytes, be 16 bytes, and so on and so forth, right? In the RAM model, theoretically speaking, this is something called a word. So in the theoretical word, this is called a word. A word is an abstract concept that refers to a particular unit of data. So it could be 8 bytes, it could be 16 bytes, sorry, could be 64 bytes, could be 16 bytes, doesn't matter, some constant number of bytes. That's what we call a word. And the RAM model says the following. It takes you constant cost, the same cost, to access a word anywhere in your memory space. Doesn't matter whether it's the first word, 10 millionth word, and so on and so forth. It always takes you constant cost. You follow me? And that's why it's called random access memory. You can do random access without worrying about having non-uniform cost of reading a particular word. Okay? It's a simple model crucial for access, for success of computer industry. Many algorithms that we have designed are based on this model. For example, all the sorting algorithm you guys have learned so far is based on this model. Quick sort, bubble sort, merge sort, all these are based on this particular model. When you see the cost of sorting is n log n, you are assuming random access cost is constant. Right? Because you only quantify the number of operations you have done for a sorting, which is n log n roughly. Of course, legal completion. You never differentiate that the tens operation might be slightly more expensive than the hundredths operation. Do you realize this? The reason you can make this simplification is because you are using the RAM model, where you assume uniform or constant cost for any single operation, as far as reading data concerns, reading or writing data concerns. That's why you can simply say it's n log n operations. You follow me? Okay? But in reality, if you think about in physical world, this might not be the case, right? Suppose this is two words. Of course, they are not the same. So two words, word one, word two, they are identical, right? In physical world, obviously it's not, it doesn't follow the RAM model, right? I place one here, I place another one right here. And when you say I want to read one word, the cost of reading one word is obviously different in a physical world, right? I read this word, the cost is this. If I try to read that word, what's the cost? And this is the cost. Obviously, the second operation is much more expensive. And this is very different from the RAM model, where you're assuming reading any word is the same cost. And that's why you come up with this n log n, all this analysis in your typical algorithm setting, right? But in reality, if that were the case, you cannot simply say the cost of the algorithm is n log n. Do you follow me? Even though it's two operations, the cost is not necessarily simply equal to two constant costs. It could be 1 for this and 10 for that. Okay, and maybe 100 for reading something over there. So in reality, we know RAM model may not hold. But then why people still use RAM model? Because in memory, this goes back to the physical property of a memory. Do you know how a memory is made? What's the physical physics? What's the physics governing the operation of a memory? I don't know the detail either. I'm not a physics major, so don't feel shy or puzzled when I ask you this question, because I don't know the answer either. But I know one thing, which is data in memory are represented by electron signals, positive charged particles and negative charged particles. That give you 0 or 1, right? Positive is 1, negative is 0. So when you access data in memory, it's done by electrons. And what's the speed of electron? Do you know? What's the speed of electron?
Same as light.
Close to the speed of light. Not same as the speed of light. Close to the speed of light. Do you know what's the speed of light? It's some big number, right? So when you memory this small and things traveling the speed of light, yes, there's a difference for reading data here and there, but that difference is, I cannot detect it. If you can, well, let me know. I want you to sign my notebook before you become famous next minute. Okay, so that's the point. Okay, but in reality, we don't have this, right? In reality, what do we have? We have, sorry. In reality, we have this, rather. We have a hierarchy of memories, like this, organizing L1, L2 cache, and RAM, then disk. Okay. So speaking of disk, this is an abstract view of disk. So it's organized in a cylinder kind of shape, and it has this concept called track, and it has this magnetic surface that stores magnetic field. That's either 0 or 1. Then there's a spindle moving in and out and reading data. Reading data and writing data means that convert a magnetic field, either north or south, into electrical charge particles, positive and negative. So, for example, north magnetic field may translate to 1, and the other will be translated to 0, right? So that's the kind of the basics of this. So the point is, when you have this spindle, right? This mechanical structure that's responsible for reading data and writing data to and from disk. When you try to read data at a particular location, you have to move this thing in and out. Let me show this again. So your initial location was there, but the data you try to read is on another track, which is that dotted line, dotted circle. What happens? You have to move that spindle. You have to move that. Oh, sorry, this is not called spindle. This is called the arm of the disk. You have to move the arm in and out. You follow me? Like that. And this is a mechanical movement. It happens really fast, much faster than the way I showed you. Because if this really moves that slowly, we won't be here today, right? Computer science won't be an industry. Nobody will use computer when you move that slow. It's really fast, but still, compared to the speed of light, which is what main memory, the electron moves inside main memory, the speed of that, it is kind of like this, relatively speaking. So it is much slower to read data and write data to and from disk for that reason, because this is a mechanical process. No matter how fast you cannot be even close to the speed of light. Okay. Okay. So that's kind of the high-level intuition, and in this class, we will not take this view. We will not take this view either, because as I said, we will abstract away the cache. So the view we're going to take in this class is essentially this view right there. CPU, memory, and disk. Okay, that's the model we're going to operate in. Do you follow me? Okay, so, and there is a scalability problem, which is when you start reading data from this memory hierarchy, what happens? Initially, it's really fast. There's one point, it will simply shoot over to the top. And that happens when the amount of data you try to read exceeds the capacity of your memory. That's when you have to start accessing data from disk. You notice this kind of sudden increase in the cost. Okay? Do you follow me? If you look at this curve, this is, by the way, this is a cumulative curve, total running time. So from here to here is roughly linear. That satisfies the RAM model. Linear to the data size, right? So that's the RAM model. Time taken to read any particular amount of data is constant. So that gives you a linear curve. Of course, you may argue, wait a minute, this is not really a linear curve. It has this up and down a little bit. Well, it's a system. Other things kick in. You're never gonna get a really linear curve, right? But roughly it's linear, right? So it's satisfies the RAM model. But then from here to here, it no longer satisfies the RAM model definition, right? So it's no longer constant cost for accessing the same amount of data. That's because disk kicks in. So there are some concerns. I will leave this for you to rate. let me go right into the, so talking about data transfer. What are some concerns on data transfer? I think you can read this yourself, and will be able to appreciate this once I introduce the concept of disk and buffer to you. Okay. So this is a high-level picture of database kernels, and we are essentially at this place right here, disk space manager. So in order to understand disk space manager, we have to understand disk first. So database management systems store information on disk, and from an abstract point of view, a disk needs to support two and only two operations, which is read and write. Whether you read $1 million or you read $100, it's just some bytes stored on disk. I don't really care what's the semantics of those bytes. I only know you need to read this 100 bytes from this particular location, whether that 100 bytes represent a bank account value or a student name or something else, I don't really care. And you read that 100 bytes, you do some sophisticated operation, whether it's as simple as plus 10 to it or as expensive as doing a square root, then exponential, then log, whatever coming back. At the end of the day, you tell me to write another 100 bytes back to that location. I don't really care what you have done from the disk point of view, read and write of certain amount of bytes from particular location. That's the abstract view by the disk. Okay? So why not store everything in main memory? Well, it costs too much, and main memory is volatile. You may lose data when your system lose power. So this solution is not really a good solution. It's not really a good solution. Well, the picture is changing though. If you think about, if you go to Google and Microsoft, all this Facebook, all these companies with large amount of data, they do try to store everything in main memory nowadays, but not on a single machine, but over a cluster of machines. Things like Spark have been designed for that purposes. But even in those systems, you still have the problem of these two challenges. One is data are still volatile, so you still need to somehow back up your data at some point so you can recover your system state when the system fails, and it still costs too much. So they have to go with a hybrid approach of using a lot of memories with a lot of disk. So it's more like a hybrid approach rather than you simply don't have system nowadays that's purely all memory based. That's just impossible given the amount of data we have to deal with today. Okay? So solution number one is not a good solution. It's too expensive and not very scalable. Okay? Well, it is a I should correct myself. I don't want to say this is not a good solution. I think the better word to use is this is not always a viable solution. That's the word to use. I mean, it is a good solution. If you have the money to buy this many chips and your data can fit entirely in main memory, and you have a way to back up your data, not only back up your data, but back up the state of your system, because you do computation on your data, right? So those states change over time. You have to remember those states somehow on a non-volatile storage medium, because otherwise when the system fails, you lose all the intermediate states of your system. What happens? Well, you have to go back, even if you have your data in a non-volatile medium. All these expensive computations you have done so far are completely wasted, lost. You have to redo those computations from scratch by reading data from disk to memory again. If you try to do that every single time, it's too expensive. You follow me? It's too expensive. Okay. So that brings up the next player called disk. For disk, we're going to talk about both magnetic field disk, which is the traditional disk, and SSD, solid state drive disk. We're going to talk about both of them. So let's start with magnetic disk. Main advantage over tapes. Tapes, I mentioned, is really cheap, really large storage medium, but only supports sequential access. Disk does support random access. What do I mean by random access? I will explain that in a minute. First of all, data is stored and retrieved in units called disk blocks of pages. Disk blocks of pages. And in this class, we're going to use a block and a page interchangeably. So they refer to the same thing. Whenever I see a block or page, they refer to exactly the same thing. It's just a unit that disk operates over. Okay. Unlike RAM, time to retrieve this block varies depending on the location on disk, like the simple experiment I just did. Okay. So here is a picture of a disk, magnetic field disk, by the way. So So what happened is you have this arm assembly. This thing move in and out, like what I showed you earlier, like right here. That's the arm assembly, okay? That's the arm assembly. And this picture shows only one arm, in one arm, what I call arm hat, one arm hat. In reality, you have multiple arm hats, multiple arms. Each arm has an arm hat, and it's all attached to something called arm assembly. That big structure right there. That's called arm assembly. This is the particular arm. This particular part is called the head of the arm, or arm hat. Okay. The arm hat is denoted by that black small rectangular region. It's a particular physical structure that's able to convert magnetic field to electrical signals. So north and south become positive and negative signals. Then that's how you convert 0 and 1 from this to 0 and 1 in your memory. The detail of this, I'm not going to cover it. If you're interested in this, you can go and talk to some guy from computer engineering or electrical engineering. They can explain it. Hopefully they can explain this to you. Right? Okay. So, but for our, as far as we are concerned, you only need to know that this thing can convert from magnetic field to data in your memory. But the point is, you have to move this in and out to align this black region, to align that well with the data you're trying to read. Okay, so where data locates at on disk? Well, on a disk, you have multiple what we call these platters. So this is one platter, this is another platter, this is another platter. So each platter has two surfaces, up and down, and those are magnetic surfaces. So they can store magnetic field, north and south. Okay, and then each platter on each surface, data are organized into what we call tracks. A track is nothing else but this circular region has the same radius to the center of the disk, which is that spindle right there. So all the surface region have the same radius to the center of the spindle, forms something called a track. Okay? On a particular track, you have multiple what we call multiple sectors. So each this small kind of like rectangular shaped region is called a sector. A sector typically is 512 bytes. 512 bytes. A different disk manufacturer might change this value slightly, but typically it's 512 bytes. A consecutive region of 512 bytes with same radius to the spindle forms a track from a magnetic surface on a platter. You follow me? Okay. All tracks from all platters with same radius to the spindle form what we call a cylinder, which is totally a conceptual thing, right? It's not a materialized object. It's just this conceptual cylinder over there with all the tracks with same radius to the spindle form what we call a cylinder. So you're gonna have multiple cylinders. One cylinder, second cylinder, third cylinder with increasingly larger radius all the way to the edge of your platter. You follow me? So that's your disk, okay? The way you're gonna read data from disk is as follows. The spindle will keep spinning at one direction, clockwise or anti-clockwise. So the spindle will spin all the time. When the spindle spins, it takes all the platter rotate with it together. So all the platter rotate in the same direction when the spindle rotates. Okay? And the way you read data is to align, for example, you want to read this sector right there. How do you do it? Well, you have to make sure the arm height from your arm assembly for that surface is aligned with that particular track. So you have to move in or out of this arm assembly so that the arm height is right above that track. But that's not enough. You also have to wait for that sector to be rotated under the arm height. For example, I have moved this in so that this arm height is right above. In order to read that sector, I still have to wait for that sector to be rotated right under the arm height. You follow me? So you have to do this first. And then wait for this thing to rotate right under this, that arm hat. You follow me? Alright. So that means that the next thing you want to notice is on a disk, you do not read data by sector. You do not read sector by sector. What you do is you read page by page or block by block. So what's the concept of page or block? When I say I read a page of data, I read a block of data. A block or a page is nothing else but a consecutive collection of sectors from disk. A consecutive neighboring sectors on disk. Neighboring sector on disk form a page, form a block. Typically, a block or page size is defined by the disk manufacturer, but typically it's either 4 kilobytes or 8 kilobytes. That's a page or a block. So if you have a 4 kilobytes page, what happens? That's just consecutive 8 sectors on that surface. You follow me? If it's 8 kilobytes, then that's just consecutive of 16 sectors on that disk surface. If, of course, each sector is 512 bytes. Okay? Now, next, I'm going to introduce the concept of next page. When I say, okay, you read the first page, then why don't you read the next page? What do I mean by the next page on disk? The next page on disk refers to the next page from the same track. If you run out of pages from that track, then it goes down to the next track, but on the same cylinder. When you run out of all pages from a cylinder, you go to the first track of the next cylinder. This concept continues on. That's the concept of next page. So you start from, for example, this page. Let's say I have 8 sectors, that's one page. Then the next 8 sector, that's the next page. Next 8 page, that's the next 8 sectors. And then I run out of all sectors from this track. What do? I go to the next track, but from the same cylinder. So that's my next page, next page, next page, and next page, next page. When I run out of all pages from the cylinder, I go to the next cylinder. You may wonder why you define like that. Why you define next like that? This is really to honor this concept called sequential access versus random access. So now let me introduce this important concept of sequential access versus random access. What do I mean by sequential access? Well, if you're reading pages sequentially next to each other from disk, that's called sequential access. If you're reading a page from here, then move the arm hat to another location, read from the random location, that's called random access. There is a huge difference between the two, because for sequential access, what happens? You move your arm to be aligned with that track. You wait for the rotation, for that first page to be rotated under the arm hat. After that, what do you do? For the most part, your arm stays still. You don't have to move the arm, because you simply wait for it to rotate. You only need to move the arm again when you have finished reading all pages from this cylinder, which is a lot of them. Then you move the arm, even if you do have to move the arm, you move the arm a little bit to the next cylinder. You don't move the arm to far away cylinders. Versus random access, you read the first page, you have to do this, finish reading this page, finish, meaning when those 8 sectors rotate over the arm hat, what do? You have to move again, wait for the rotation. Move again, wait for the rotation. Much more expensive. Okay, I have a picture to show that. Then I will let you go. So this is a simple experiment I have done. This DD workload is a sequential. You can think about this as a sequential read workload. So I sequentially read, I have a file that's located on disk sequentially. I read this file sequentially. Y-axis shows the offset of the page I have read from the disk. Offset of that page I'm going to read from the disk. Y is the time. As you can tell, for sequential workload, what happens? You keep going, then sometimes you have to move Again, that's what will happen when you have read all this thing from one cylinder move to the next cylinder, so the offset change dramatically. But then it continues. Do you follow me? That's sequential workload. What about random workload? This is the same experiment, but now I show that sequential workload together with a random workload. So I'm running both a sequential rate and a random rate at the same time. You can clearly tell that's your sequential workload. What about those other dots? Those are your random workloads. Those are your random workloads. If you continue this experiment, what happens? If you keep adding random workload to it, what happens? And this is what happens. Your sequential workload is totally destroyed by that sequential, by those random workloads. Why? You only have one disk arm. Typically, a disk will do round-robin service to its request. So I will serve the sequential workload a little bit before switching to that random workload and coming back to the sequential workload. If you have one sequential workload, one random workload, that's okay. When you switch back and forth, the sequential pattern is still very much preserved. But if you have too many random workloads, it takes too long for the round-robin to come back to that sequential workload. By that time, the disk arm is totally misplaced. It's no longer a sequential workload from the eye of that sequential workload. Do you follow me? And by this, you can design an attack for cloud users. Suppose you store your data on Amazon.com, Amazon cloud, and they charge you by the amount of time you use their service, right? You run your sequential workload like this, really fast. 10 seconds, 20 seconds, you're done. I notice that I will purposely launch some random workloads on that disk. You may wonder, how can you do that? Well, it's all virtualized, right? So I have another virtual machine running on the same physical disk as your virtual machine. And whenever your virtual machine starts running sequential workload, I will run many random workloads on my virtual machine. Then you suddenly, for the same workload, you have to pay 10 times more money to Amazon.com. So who might be doing this? Well, okay, I reached a deal with Amazon. You pay 10 times more to Amazon, right? Okay, Amazon, you take 10% of that, I will take 20% of that. That really happened. Okay, with that, I stop right here. We continue on Thursday.